Thank you. It's almost like being back in Scotland being introduced like that. Right, yes, so today I'm gonna do a brief sort of overview of deep learning, current sort of very, very brief overview of what the current state of machine learning is. It's a bit too big to cover in a single hour, and then I'll present it in a solar context, so based on the work we've been doing with it, focusing in particular on our invertible neural network rad inversion, which is focused on inversions of solar flares. Okay, so what is machine learning? It is, and this is, I find at least, the best way to frame it. It's a way in which we do not explicitly program the computer to learn a task. How to do a task. Instead, we let it learn in the framework of a very generic algorithm that the computer itself learns to fine-tune by using statistical techniques. So, for example, if we wanted to train a computer to classify these images of cats and dogs just based on the images, we take some input training data, which is pictures of cats and pictures of dogs, and we label them, and then the computer itself learns how to map from one to the other by effectively tuning an incredibly generic, incredibly vague algorithm that we give it, which is just the form of the network that it's given. But it itself is going to learn the process by which functionally you go from there to there. And it's that makes machine learning so flexible and why it has been such a big thing in these past few years, really. So, machine learning can broadly be subdivided into four categories. So, there's classical and deep machine learning, which we'll discuss the distinction of later. But then there's also how you train your network. And so that is split into supervised training, which is where you know you have a set of data and you know for each of those inputs what the output should be. So that's exactly the case of the previous example. There's also what's called unsupervised and the slightly more complex semi-supervised side, which we'll be discussing a bit later with the invertible networks. But unsupervised is all of your dimensionality reduction techniques. So things like principal component analysis actually comes in there. That sort of thing, clustering nearby things into classes where the machine is just given a collection of data points that mean something, and then you say, try and pick out the ones that are closest on a particular manifold defined in a particular way. And so you don't know what the ground truth answer is there. You're asking it, which is why it's unsupervised in that sense. So today we're focusing on the deep end. And I'll start off by discussing the supervised side, and then we'll venture a little bit into semi-supervised, but that is really quite a big topic. So the very first sort of use of machine learning was Rosenblatt's Perceptron, which was 1957, I think. It's a very simple linear model, which takes a set of inputs and combines them with some weights, and then applies some activation function to produce an output. So what this actually means, so this activation function in the original case was simply if the weighted sum of the inputs was less than 0, return -1, and if it was greater than 0, return +1. It was a binary classification. And in fact, the original application of it was trying to classify very, very pixelated images of people's faces to try and tell what sex they were. But the sort of, this is the basis of where most machine learning comes from that we use nowadays. And the sort of the fundamental step that was the training algorithm, which is encompassed in this. So what we do is we start off with randomized values of W, the weights that are applied to our inputs. And then, given that we have a labeled set of training data, we can slowly adjust these weights to become optimal by taking the weights of the previous iteration and taking the distance between the expected label and the actual label that we find, and taking a small step in that direction, which that small step is eta, which is often known as the learning rate. And nowadays, the way we train neural networks is very similar to this. It's a generalization where instead of this linear term, we use the gradient of a certain loss function applied to the output with respect to the inputs instead. But this idea, and originally this was all implemented mechanically, which was an incredibly amazing machine where all of these weights were actually potentiometers, and at the end of each training epoch they were all twisted a bit by a motor until this optimization process ran its course, which was quite an incredible feat of sort of electrical mechanical engineering. Okay, so that's only good if we have something that's a linearly separable problem, or a linear regression, which is not a very interesting model, really. So to increase the complexity, we can stack those neurons, as they were called, because at the time they were based on sort of the best model of a neuron that we had. And if we stack these by effectively just running multiple different neurons with different weights in parallel and then recombining their outputs, we can actually start to learn nonlinear functions, which is great. So now we're making progress. So it was proved by Savenko in 1989 that using this method where your activation function, instead of just being the sign of the output, is now a sigmoid, it was proven that this, if you make a theoretically infinitely wide neural network, can learn any function to arbitrary accuracy. So it's nice to at least have some theoretical proof, even if it doesn't really let us solve the problem, but it does show that it's possible. And it turns out that in reality, yes, you do need exponentially increasing widths of wide layers to actually make that work if you're only trying to use a single layer network like this. But it is definitely nice to know that we can learn anything using that approach. So this is where deep learning comes in. And just due to the complexity of trying to figure out that sort of weight update scheme, the process stagnated a lot. And so we're sort of really into the mid-90s here by the time, even though the first research was done in the 50s, because it was difficult to figure out actually how to train these things reliably. So deep learning is simply using a deep neural network. And a deep neural network is a neural network that has more than one hidden layer in the middle. It's an incredibly simple definition and actually very vague, and most networks that you end up building will be deep. And what this actually does is where each layer is taking the input from previous layers, it's actually increasing the complexity of the representation, and we can train multiple parts of the representation at the same time in the process of training the network. And so this massively increases the convergence rate that can be obtained, as opposed to just using those infinitely wide networks which are only using one internal representation. So instead of having that single bar of neurons, we've now got multiple ones. And exactly how you connect them between each other is going to depend on the network, which we're going to talk about now. So I'm going to just simplify this greatly and say, on the whole, we have two main types of deep neural networks. There are, or layers that are used in deep neural networks. We have fully connected layers, where every neuron in one layer connects to every neuron in the next layer. And so that means that each neuron is receiving the dot product between a set of weights and all of the neurons of the previous layer. And so actually we can represent the transition from one layer to the next layer as a matrix times a vector, where the vector is the output from the previous layer. And then each row of the matrix becomes the weights corresponding to each neuron. And then we apply some activation function to that, because otherwise what we're doing is stacking linear transformations, which by definition is linear. So not very useful. So these are great and can learn a lot of complexity, but also for any sort of high-dimensional problem, they require a massive amount of memory to work with, just due to all of those matrices that we have to drag around. Also, there are certain problems they don't work so well for example, image-based problems, for which we would typically use convolutional networks. Now, the idea for convolutional networks came from, well, it actually came from the receptive field of how humans see things. But if we just think about it, if we're trying to detect a cat in the image, it doesn't matter if the cat's over here in the image or over here in the image, it's still... and the process of doing that detection should be the same whether it's here or here. It doesn't matter where a feature appears. And so what we actually do is we define much smaller kernels, and these sweep over the image. And so this process of sweeping over the image and then activating the results of that sweeping produces what's called the feature map, and so we can see, oh look, the feature map was activated to a higher degree here. So in a deep network, that is then a representation that goes into the next layer. But it's essentially saying whatever activated the feature was in this region, and so we can do more than just identify whether something's there. We can also quite easily identify where it is in the image using this sort of approach. And convolutional networks are great for image and, in many cases, time series data, because we don't exactly need to know where, when an image, in the data set, something occurs. We just need to know that it occurs, and possibly then from that find out where that was, but we don't need to a priori know going into it what the exact form of that's going to be. Also, they use far less memory because these kernels are much smaller than the size of the image we're working on, whereas if we were working with fully connected networks, the size of each layer would be sort of the same, or within an order of magnitude the size of the image. So they can be trained much faster for this sort of data. Neural networks, of course, have their limitations like every method, and these limitations are actually quite significant. So, deep neural networks can only be used for classification and regression, which, if you want to get picky, you can probably actually say are the same problem, because classification is simply a regression with a fixed number of finite classes. Whilst you can try and approximate processes which don't really belong to these categories, there is no guarantee that the results are correct. And we do need to be careful about that sort of thing. They can certainly appear so, but it's very easy to, in fact, have just overfitted whatever you were trying to learn, as opposed to actually learning how to deal with the problem properly. One of the other problems with deep neural networks is that above about 6 to 7 layers, the way in which we compute the gradient of the input with respect to the output, that can be quite difficult, just due to the fact that we have to carry this gradient back through each layer. And so we can either get gradients that mean that this explodes, or gradients that mean that this vanish. And so one of the big breakthroughs in this was in around 2011, when the concept of residual blocks came along, which is the idea where we either concatenate the input so we effectively define the network as a series of functional blocks, where each functional block is a deep neural network of some form or other, and then we also allow these bypass strips. So this is the whole residual block in blue, and then the functional element is yellow. And then we also define this sort of bypass, and so we either concatenate this input onto the output of that block, in which case, obviously, then that gradient is flowing right back through the network, or we instead, or we add them together. And so at that point, the functional block is effectively determining the correction, which is why it has come to be known as a residual block, because it's determining a correction to that. So there are sort of many problems like that as to why a network won't necessarily learn, and we are sort of starting to make progress in how to get past these. So I'm going to present a paper by my colleague John Armstrong, who this was some work that was done using inode SOT data, as we'll see, and the idea is to classify the features in images. And whilst it seems like it's quite a basic task, but also it's useful to be able to take a data set and say, show me sunspots, and identify very rapidly. As we'll see, actually, this can be done very quickly, and we're only getting more data now. But this also, and I would encourage people to read this paper if you actually want an overview of sort of deep learning and how it fits into solar physics. I feel it's actually a pretty comprehensive overview of deep learning, but not from a computer science background. So sort of really aimed at people like us who want to understand this stuff. So the idea is that we can very, very, very quickly identify all of the things in different sets of images. And so this was trained on Hinode SOT data using a 13-layer convolutional neural network, which was pretty much an off-the-shelf design. The original design was designed for full-color images. Obviously, grayscale images are typically actually harder, and what we have is effectively grayscale images most of the time if we're just working with continuum stuff anyway. But we actually get greater than 99% accuracy on our training set, which was, I think it was around 15,000 images from memory taken from the Hinode archive. And yeah, it takes less than 10 seconds on a very mediocre GPU to classify 1,300 images in our validation set to that accuracy. And so what am I talking about? So one of the nice things that we actually get out of this is we don't just get, this is a prominence, for example. We don't just get that. We get, this is my confidence that this is a prominence. This is what the network returns. And these are actually log scale histograms. So that's 10 to the minus 35 down the bottom there. It's very confident in that being a prominence. But one of the nice things about getting these confidence values is that we can actually we can flag up ones that don't have great confidence. There were some with multiple weird combinations of things in the field of view, and it was obvious from the output that the network, whilst it did pick a class, because it will always pick a class, it was very easy to flag up which ones we're not quite so confident about, and then actually just have a human look at them. And it's a vanishingly small percentage, and makes the task of actually sort of finding that data so much easier. But also, and this is one of the things this paper goes into in quite a lot of depth, is this is an extremely valuable tool for other more complex machine learning projects. So transfer learning is a very important field in machine learning, which is where we effectively work on, we use a pre-trained network of some description. So in this case, this is a network that knows what the sun looks like in H alpha. And so we can use that to guide other networks. So for example, one of the projects we've been working on is something that helps to correct for seeing. And this classification network is incredibly important in that, because the features from, say, the second, third to last layer in that are in fact a very compact, dense representation of what the sun looks like as far as this network is concerned. And so when we're sort of effectively taking in a noisy input and generating an image that supposedly has seeing corrected, by comparing this against a ground truth and using the features from this network, we can have a very good idea as to whether it looks like the sun, without sort of having a human say, yes, that looks right, because it's also providing in the way it's constructed, it also provides a way of saying, this is actually how you need to improve to look more like the sun, which obviously a human would find very difficult to encode. Go for it.
In that network, does it define its own classes of machines?
These were predefined classes.
Predefined by you?
Yes.
Okay, so is there a way to make it define its own class?
Yes, there are ways to make networks define their own classes. That is getting into an unsupervised form of learning. And we did, in fact, have trouble for a while, from memory, between filaments and prominences, for obvious reasons, because they are a class. The difference between them is arbitrary, and so a network wouldn't necessarily have defined that sort of class boundary in the same place as we have physically defined them. And I think, yeah, there could be some interesting sort of subdivisions of categories that could be done entirely automatically like that. Any other questions before I move on?
I have one.
Go for it.
So that was that
it needs there is some flexibility. It can't go if you give it an image that is orders of magnitude higher in spatial resolution, it won't work unless you compress that data. But for plus minus a factor of a few, yes, it works absolutely fine. Although the paper does an experiment where it puts in some UV, I think it's 1600 data, and it shows that actually, shockingly, the sun doesn't look the same in all wavelengths. And particularly things like the brightenings around the sunspots in UV really throw it off. But other H-alpha data sources should absolutely be fine. So I'm going to talk now about sort of our approach to inversions, and particularly in the context of solar flares, where we've really been lacking in inversion tools, as I'll explain. So how we deal with inversions normally is, I quite like this flowchart. I didn't make it, but again, credit to John for this one. So we start off with some initial guess distribution of the atmospheric properties, and now that's typically some sort of semi-empirical atmosphere. For the particular line we're trying to fit, we solve the forward radiative transfer equation, and we get some line profiles, and then we calculate the chi-squared between that and the actual line profile. And it's probably not a good fit, because that was the first time we've done it. And so we then, based on that chi-squared, we calculate some response functions, and we modify the atmospheric parameters until eventually we get a fit that we're happy with, or the computer gives up. And that process is how, at least I would say, is how from inversions we try and infer some atmospheric properties. Now, the problem is you typically, particularly for flaring stuff, is you typically in these inversion codes make a lot of assumptions on things like hydrostatic equilibrium, which is really not a good assumption when we've got an atmosphere moving at 300 kilometers a second that we can infer from Doppler shifts. And there's also the fact that it's been very well shown that that atmosphere is not in statistical equilibrium. So without being able to make those two assumptions, you've got such a giant parameter space over there that it's nigh impossible to search using traditional techniques. So we decided to tackle this from a different way. So first of all, we're going to have to do a bit of maths. So inversions themselves are not a well-defined function. So what that means is that for a given set of synthetic line profiles, there are multiple atmospheres that can generate them. Now, exactly how big this degeneracy is and where it lies, we don't entirely know, but we know that this degeneracy exists mathematically. And so, whilst this forward process is a perfectly well-defined function, that function is not bijective. Which means that for a neural network, we actually have a problem in that we can't learn the inversion. Because if we're learning the inversion, we're not learning to approximate a well-defined function. And so what we can end up with is it's been proven, either if there's multiple modes that could possibly have generated that output, then the network will either learn one of them, or it will actually quite frequently learn an average of them, which is even worse, because physically the average of those atmospheric modes has no meaning whatsoever. So we try and sort of break this degeneracy by augmenting our intensity space with a latent space. Now, what this latent space is, we'll come back to, and it's a little bit of a pain, but effectively we define a latent space that matches the intensity space, and then we actually have a well-defined bijective function between these atmospheric parameters and the outer product of these spaces, effectively the combination of these spaces. And so defining this bijection is fundamentally what makes this a problem that can be treated nicely using machine learning. Or at least in the very general sense that we're trying to treat it. And so the training scheme, it turns out, for a network like this looks an awful lot like the inversion. We put some data in, we see if it's good, and if it's not good, using that gradient descent scheme, we update the weights, which is very similar to what happens in an inversion. So in many ways, using a neural network in this way is like forward-loading the cost of your inversion into a training, as opposed to sort of running that every time. So if we take, this is a fully connected feed-forward neural network, very standard. So this is the fully connected kind that I was discussing earlier. Now, if these layers are the same dimensionality all the way through, which they're not in this picture, but if they were, we could, and if we had a activation function between each layer that was smooth and that we could take the derivative of, then we could actually invert that by, for each layer, we take the derivative of it, and then we invert the matrix, because the matrix is square, because there's no change of dimensionality between the layers. And we could have a very expensive way of defining that neural network as a bijective invertible function. However, as soon as we have any change of dimensionality, that goes out the window, because what is the inverse of a non-square matrix? So, turns out what we can do is we can define what is known as the affine coupling layer. And so this is from, this was first proposed in 2014 and then extended in 2016 as a way of, the original application of it was for looking at probabilistic inference and a very pure class of inverse problem compared to what we're dealing with. And it wasn't really until a paper in 2018 by Ardizone et al. That this was applied to some sort of physical inverse problems that we would recognize as such, as opposed to sort of very mathematical constructs. So if we define four functions, S1T1, S2T2, then we can build an affine transformation that is bijective using those four functions. And those functions themselves, we've said nothing about them other than that they be well-defined functions. That's the only requirement on them. But by combining them, and so what you have here is the forward mathematically and the diagram of the forward. And some people prefer the diagram, some people prefer the maths. We are using O cross to denote element-wise product and O slash to denote element-wise division of matrices, and tensors, technically. And so we take an input, x, we split it in half to make x1, x2, and then we pass it through these s and t functions. And then this gives us y1 and y2, and then we recombine them just by concatenation, because these are vectors of a certain length. And we can very easily on paper write the inverse, write x as a function of y. And it turns out, that this is invertible for any well-defined S and T with no requirements on the invertibility of S and T, which is lovely. So that means we can just use any form of deep neural network that we want to approximate these, and we've suddenly got functions that we can train to better match our inputs to the desired outputs. Okay, so we can actually stack a bunch of these and make a whole network, and it's possible, thanks to the magic of all the time people have invested in deep neural network frameworks, to compute the gradients all the way back through that in one go, and it's actually not anything like as hard as you would expect. The amount of code to do that is shockingly small. And so we can train those S and Ts to match exactly what we want them to be. So great, we've got a technique that can match any well-defined process. And okay, it needs to be a well-defined bijection. And as we said before, the bijection for radiative transfer is not well defined, but we have that latent space. Now, so what we're doing is we're increasing the dimensionality of the output space, where the output space is whatever intensity vector you get out. And we increase it, we augment this with a space that doesn't have any obvious, that doesn't really make any obvious sense. It's not physically intelligible yet, although there is plenty of pure ML research working on the concept of trying to interpret these things. But currently, it's actually noise. We augment the data with an additional vector of noise, which is drawn from a random, an n-dimensional unit Gaussian distribution. So effectively, for each input set of atmospheric parameters, we generate the output intensities and a vector of noise. And that means that when we're going backwards through the network, we put in a vector of intensities and a vector of noise. And that maps then to a unique atmosphere. And so conditioning this noise to be of the right form is actually quite difficult. And that's where most of the maths comes in here. So that can't just be random noise, because what we want to be able to do is draw multiple samples of this noise, attach them to the same intensity vector, put that through the network, and get a set of posterior distributions for what our atmospheric parameters were. And because of the well-definedness, and if we sample the noise space enough times, so that's why we want a nice, smooth, easily sampled distribution like the n-dimensional Gaussian, we, in theory, sample enough of the posterior distribution of atmospheric parameters to have a good understanding of what's going on there. And so to do this, the latent space needs to be independent of the output space. And what that means is that for a certain generated intensity vector, the latent space has to be able to vary. The two need to, so if we have two atmospheres that generate the exact same intensity vector, they have to generate different noises, otherwise we haven't achieved this bijectivity. And this is done by going through the wonderful reproducing kernel Hilbert space, which I'm not going to do the maths for. It is in the paper, and you can ask me afterwards if you really want to know. I don't promise to remember all of it, though. So effectively, what we end up using are some very nice results that came out of some statisticians, which is effectively applying kernels to samples of two different distributions. We can find arbitrarily high-order differences between those distributions. And so what I mean by that is if we have two different Gaussians with different standard deviations, or with different means, then we use a first-order difference, because the feature we're looking at is the mean. It's first order. It's very easy to find the difference between them. If we've got two Gaussians with different standard deviations, it's a second order. It's the variance we're looking at that point. So that's a second order feature we're using to find the difference between them. If we start to try and find, or if we want to find the difference between, say, a Gaussian and a Lorentzian with the same mean and standard deviation, it's getting harder. We start to need higher order features to sort of mathematically, automatically determine what is the difference between these distributions. That's difficult to quantify, I would say. And so this is a generalization of that, where we apply these kernels to the samples. And the reproducing kernel Hilbert space gives us a way to write the dot product between these features, between infinite numbers of features in a closed form that we can actually compute. And so, for example, if we were to use a Gaussian kernel like this one, these are our first three features, and they carry on like this. And as usual, the first feature is the dominant feature, and then the higher order features become less and less significant, and that's the form of all of them if you want that for some reason. So that is actually, that's the mathematically sort of difficult part of that training data. Obviously, okay, we need to learn a model, so we can't just sort of say we're going to go from some atmospheric parameters to some line profiles, and then we're going to go backwards, because how exactly are we going to get these atmospheric parameters and these line profiles, particularly for flares where we're not assuming hydrostatic equilibrium and we're not assuming statistical equilibrium. Okay, so we use the RAD encode from Carlson, Allred, Kowalski et al. So this is a one-dimensional radiation hydrodynamic code that does non-LTE radiative transfer with complete frequency redistribution, and time-dependent level populations, which is very important for flares, and even in sort of slightly more active regions. The early Carlson papers showed that it can take thousands of seconds for hydrogen to settle back to statistical equilibrium after you perturb it a bit. So what we do is we extract a very small amount of information that these simulations generate, and the FChroma project was nice enough to have previously run a wonderful grid of about 90 of these simulations that we were able to use rather than run them all, and we since ran some more, and yeah, that was a lot of computing hours. So what we take out of these simulations is we take effectively 5 parameters out of these simulations. We take the electron density at 50 height points, we take the temperature structure at these same 50 height points, we take the bulk velocity at the same points, and then we also take the 2 line profiles that we're going to be using in these inversions, which are hydrogen alpha and calcium 28542. 20% of this data, which is selected randomly from those sets, we chop off and we make it. We chop off and we never let the network see it. So this is what we use to check whether our network is actually going to generalize. And obviously, yeah, we're generalizing on, but at least checking that we've learned our own model properly rather than just overfitting everything. Things like microturbulence aren't treated in here because Radin has an assumption of there is 2 kilometers per second of microturbulence everywhere, and so it's not a free parameter, so the same is assumed in our training set. So we actually build a network using what we've built, and so we take the input, which is those atmospheric parameters, and then we go through a series of these affine coupling layers to an output. Now, you may note that also some other things have appeared, and these are the permutation layers. The permutation layers are very simple. All they do is they randomly shuffle the elements of the vector that come through them in a predetermined way. So they just shuffle the same way every time. They're just initialized randomly at network creation, and then they stay the same. And so what that does is it's simply to encourage mixing between the 2 halves of the affine coupling layers, because these affine coupling layers, the first thing they do is split the input into 2. And so we just want to make sure that that's nicely shuffled so that everything is coupled between the 2 halves. It does work without them. You just get better results faster if you have those permutations there. And so the input goes through that network to the output, which is those 2 line profiles, which what I didn't say is that these were normalized so that the highest value in either of the line profiles became 1, and then the 2 were normalized relative to each other, so we're using the relative intensity of the 2 lines as part of this as well. And so that maps to the output, which is the 2 line profiles and a sample from the latent space. And then to go backwards, if we have a set of line profiles, we draw lots of different samples from the latent space, say 20,000, and then we put that back through the network, and we get effectively 20,000 different plausible atmospheric atmospheres that could have generated them, and it turns out most of them are very similar to each other, as you would hopefully expect. So the functions S and T that we settled on are these networks, where the activation functions are what's known as ReLUs, which are rectified linear units. They are the simplest. I would say they're the simplest form of activation function used in neural networks. They are 0 for any input below 0, and they are linear for any input above 0. So they're only just nonlinear, because the requirement for an activation function is that it's nonlinear. These are only just nonlinear. And leaky ReLUs are basically the same thing, except below 0, it's 0.01x, which just means that a little bit more gradient can seep back through the network, because the ReLUs are great in that they enforce sparsity in layers in front of them, because they chop off any input that was below 0, and so any input, or in subsequent layers, that creates sparsity, which is nice. Sparsity is almost always a nice property, because it increases the complexity of your representations. But sometimes also I think we were having a bit too much sparsity, so we let a little bit more information flow through and it learnt nicer. The inverse tan on the end is actually just a very cheat way of avoiding the output getting too big here, because the t functions go into the exponential that we're using in the affine coupling layers, and we don't want that to explode, so we limit it with the inverse tangent. So here is the ugliest slide in existence. This describes the actual training process of the network, and there's a lot of information here. Like, this is the actual sort of nitty-gritty insides of what we spend our time doing whilst we're trying to get the network to learn. So we have to define the way all of the affine coupling layers work, at least when you're using fully connected affine coupling layers like we are, is that the dimensionality of the input and the total dimensionality of the output have to be the same. And we're working on ways of escaping that, because it leads to some things that wouldn't be nice to get rid of in future, like the fact that we have the majority of the input space is actually zero padding, which would be nice to get rid of. It's just not particularly pretty. So we have 50 points in electron density, 50 points in height, and 50 points in this very strange form of velocity. And this very strange form of velocity comes about because we have to handle a very large dynamic range of velocities. We've got velocities. We need to be able to resolve velocity shifts of less than a kilometer per second up to 300, 400, 500 kilometers per second. And we eventually settled on this approximation, and it seems to work quite well. And you can easily invert it. So that's what we used. And then, so the output is 200 dimensions of that latent space, which seems like quite a lot. So it's that 200 dimensions of that unit Gaussian noise, so 200 entries of it. There is a lot of theoretical work going on about how big this latent space needs to be given the dimensionality of a particular problem. But the answer for now is nobody really knows, and so you keep making it bigger until it works. What is the intrinsic dimensionality of this forward problem? Well, I mean, it's probably at least 150 dimensions, in that we've got 150 inputs going in, but also, depending on the correlation between those inputs, it might actually be less, or it might be more, although that if it's more, it's getting a bit harder to understand if the intrinsic dimensionality is higher. So it might just be that effectively the network, because we obviously tried this with 150, and it didn't do so well. But it might just be luck, because we in the sense that we have a lot of stochastic updating of weights going on. So really trying to narrow down how big this latent space needs to be is quite important. But what you'll also notice is that we still have zero padding in this output. And so we could have got rid of a lot of the zero padding over here if we'd gotten rid of some of the zero padding over there. The reasoning for this is actually because we made these bigger, because it gives the network internally more space to represent the information over. And that allows it to generate more complex representations of the data we're feeding into it as we go deeper in layers. So each layer has a more complex representation than the layer before. But oftentimes, and there's theoretical work showing that oftentimes an increase in width can account for a lot more than an increase in depth. And in this case, it was very much shown to be true that increasing the width to this point gave us much better generalization for whatever reason, due to whatever the weights internally are doing. And then we have the line profiles with 30 points each that are normalized in the way I discussed before. So training is done through a wonderful combination of 4 different losses simultaneously. So normally, if you're training a normal feed-forward neural network, what you have is you have a set of inputs, you pass them through the network, you then typically compute the L2 loss, that one. You compute the L2 loss between, so it's the Euclidean squared loss, and then you just average it over the number of them, between what you want the output to be and the output you actually got. And using the backpropagation algorithm, you can update the weights in the middle until you eventually get an arbitrarily close, if your network's sufficiently complicated, you get an arbitrarily close match of the outputs to what you wanted the outputs to be. Unfortunately here, we need to train in both directions. And we also need to enforce that our latent space is independent of our output space, and so that's not really something we can do with just an L2, because the requirement on the latent space is that it be a sample from the Gaussian ball distribution, but not what that specific sample for that line profile should be. We don't know that. We simply know that it should be a sample of that distribution, and that is where the loss that we get from the reproducing kernel Hilbert space, which is called the maximum mean discrepancy, comes in. And so we train in the forwards direction by applying an L2 loss to the line profiles. The line profiles need to look right. And then we also, at the same time, apply a maximum mean discrepancy, which enforces that the latent space looks like, so for a certain batch of inputs, the latent space needs to look like the same size sample from that original distribution, from the ground truth distribution. And we also do the same thing backwards, so we effectively use the invertibility of the network to train in both directions to make sure that the model is well conditioned. And so we apply an L2 loss with a little bit of scaling, but it's an L2 loss, to the atmospheric parameters. And then we apply a maximum mean discrepancy, and in this case, not to the latent space, but it's to the generated atmospheric parameters, in which we're saying, so we're training, so we've given you these line profiles with a random sample from the latent space. We're training you backwards. What we need is for this network to produce a set of atmospheric parameters that plausibly could have been sampled from the distribution of atmospheres that we have in our input set. And so the conditioning is that plausibly that both of them need to look to the maximum mean discrepancy like samples from the same ground truth distribution. And yes, that we damp that in that we don't do this for the first few epochs of training because it tends to make the network diverge, and that's a purely empirical thing. For some amount of time later, that's all one, and so that term's gone. Yeah, that is. Go for it.
So the maximum mean discrepancy sounds like L1 loss.
So the maximum mean discrepancy is the distance in the reproducing kernel Hilbert space between the mean of each of those each of those features. So we get those features by applying the kernel to each distribution, and then we compute it's actually the vector distance between those two infinite vectors of features, which we convert into being an inner product, which the properties of the reproducing kernel Hilbert space let us write in a closed form by using the kernels. So it's a much higher order loss than that. Yeah. Yes.
What that really sounds to me is like you're doing k-means analysis. I mean, basically, you're doing a clustering type of analysis of the sensor data. That's what you just said. So my question was, why would you do a cluster analysis at the beginning of your parameter space before you do this?
Why wouldn't we do a clustering analysis of what the atmosphere is before we feed them in?
Yeah, then rather than going through all this stuff. I mean, that's exactly what you just said.
Uh-huh. The clustering.
Yeah. So basically, k-means cluster analysis takes your n-dimensional parameters.
Yep.
Right?
Yep.
And basically takes a reproducing Hilbert kernel.
Yep.
And it places it exactly at the mean for every cluster.
Yes.
And then it calculates the distance between every sample and that mean.
Yep.
Which is exactly what you just said.
Yes. But we're effectively using very similar maths to the k-means to constrain what is learning the function here. So it's the ability to be able to put new points into that, as opposed to just classifying a fixed set of data. So the idea is that we actually now that's simply the loss that we're using to train the model, whereas the model itself can functionally generalize beyond that classification is the idea. Well, it can only generalize based on the data it's seeing.
That's all it can ever do.
Oh, yes. I mean, it can't extrapolate.
So it's never ever going to create more clusters than you were. And it's basically like a classification. I mean, what it is, it's like doing a classification and clustering within that. I mean, basically, you're classifying to say whether, basically it's this new sample to go beyond that in this cluster, that cluster, that cluster. That's all you're doing essentially by.
I don't think that's quite the case. I think because I mean, certainly that is obviously how k-means works. But the maximum mean discrepancy itself, the purpose of it is to compute a vector difference between two distributions based on samples from the distributions. And I possibly didn't express that particularly well. And so the idea is that we are training the network to produce distributions that are as close to the input distributions as possible. Right. So we need to obviously then validate the network in both directions, and this really doesn't show up particularly well on these. I probably should have picked better colors. But okay, so for a given atmosphere input, we get a pair of line profiles out, and we have a ground truth, which is the dashed blue, and there is also an orange, which happens to be sitting underneath it, and I assure you that it's actually underneath it, and the two agree very well. So the forward process, at least for the example I'm showing you, and actually for most of the examples, matches very nicely. Okay, so for the inverse process, we end up with a slightly more complex way of representing it, because what we're doing is we have to take, say, our 20,000 samples of latent space, attach them to these line profiles, and say, what's our distribution of plausible atmospheres? And so our atmospheres here, we have two-dimensional histograms that sit below these dashed lines, and in this validation case, these dashed lines are what Radin actually said the atmosphere was, because this is our training set, this is our validation set. The network was never trained on this. This is our validation set, but we know because this was our training model. And the black bars here are actually also two-dimensional histograms that are very tight in each parameter, which is just showing the sort of the round trip from each of these atmospheres back to the line profiles. So we reapplied the forward process to each inversion to show that it's well constrained. And so we can obviously see that higher up in the atmosphere, where hydrogen alpha and 8542 don't show us very much, we are less confident about what the velocity is, which makes sense. And we got it. It's right there because it's seen lots of Radon atmospheres, so it can quite comfortably predict what a Radon atmosphere looks like. And of course, that is the caveat of this model, is that it will always say the sun looks like Radon, because as far as it's concerned, that's all it knows. So let's do that. Let's make the sun look like Radon. We've got here some observations from SST CRISP in H alpha and calcium 2. This is a lovely little M1.1 flare. We've got a circular point on the ribbon and a square point way off the ribbon, which is as close to quiet as we can get in this training set, or in this testing set. So we do exactly the process that we just discussed, in that we normalize those intensities. We then draw lots of samples from the latent space, which is 20,000 in each case, and put them back through and get our distribution of atmospheric parameters out. In this case, the black line obviously is not a known true solution, because we don't know what the true solution is. The black line here is the median in each bin, or along each column, essentially. At each height point, that's the median solution. And they seem very plausible, and they fit to a previous analysis that was done by this flare by Karidze et al. In 2015, in that we predict the right velocity shifts and temperatures based on traditional techniques applied to the line cores. Well, some of you may have noticed the noisy stuff going on here in velocity. Now, This never occurs with training data, and what we believe this to be is effectively the constraint that Radin itself placed, which is that microturbulence is 2 kilometers per second, whereas these lines are incredibly broad. It doesn't seem plausible to generate those with such a low microturbulence, and so our belief is that the network is effectively generating this broadening by, well, this bit's going to go down a bit and this bit's going to go up a bit, and effectively we've produced microturbulence. And that is our general understanding of this, because it only occurs in broad lines. It only really occurs in broad lines in true data, in real data, and we can't get it out of any of the Radin training sets. So it's possibly an artifact, but we believe it to be due to the breadth of these lines. Absolutely, yeah. Yeah. That seems perfectly reasonable, yes. And the joy of this method being so fast, due to the way it's applied, is that we can invert the whole field. So this is the whole field of a crisp observation, which is around 1,000 by 1,000 pixels. So we did this for every time step of the data set, which I think was around 618. It took about a week and a half on a moderately powerful GPU that costs about $200. So we're talking high-end, high-performance computing here. And we produced, I think it's about 6 terabytes of inversion data based on that. So that's 50 height points for every one of these. Now there are some pixels which aren't well constrained, because to do it on that time scale, we reduced the number of samples we were drawing from the latent space. However, we are also computing the maximum absolute deviation on each of the parameters at each height point. So that's effectively saying, if the parameter isn't well constrained, we know which pixels we don't have constraints on, and we can go back and use more samples from the latent space to try and constrain them further. So again, we have a way to tell when the method doesn't know well what's going on, in that we can simply look at what the width of that posterior is, and possibly even what the shape of it is. We've yet to produce any multimodal distributions with any of the data we've put in. We're very interested to find out if we can actually find some. So I think that's about it. This method of invertible neural networks can very broadly be applied to a lot of classes of problems. It's the idea of finding a functionally trainable bijection where no bijection necessarily exists normally, just by this augmentation with the latent space. I mean, for us, this was sort of the obvious choice of inversion, but I mean, of trying to sort of solve the problem of flare inversions. But obviously, I mean, we've added our own set of caveats to it, which is that now we're just generating Radin. And so whether that is interesting depends on how much you like a particular code. I mean, you can obviously train this to work with any radiation hydrodynamics code, but we're then assuming that the atmosphere is sort of column by column. Is that a sufficiently plausible assumption? It entirely depends. So we lift one set of assumptions and approximations and add a whole nother set. It entirely depends on which ones you're most happy with for a particular problem. But yeah, I'm happy to talk about the method with anyone who wants, and yeah, that's all I've got really.
Thanks, Chris. Any questions?
So, what if we reconstruct the magnetic field?
No, Radin is radiation hydrodynamic, no magnetic field. I am working on trying to do improved forward simulations of flares onto which I'm going to start imposing some magnetic fields. They're still going to be one-dimensional, and applying this method to. However, if you have a 3D MHD code or whatever that you want to use, you could train something based on this method, based on the idea of invertible neural networks, to also try and infer magnetic field. But we don't have any magnetic field data in the training model, so no, we can't infer anything about magnetic field from it.
Okay, so when you had, can you go back with the slides? I got really back, and super back. You talk about inversion.
I listed magnetic field. I did. Well, normally we do include magnetic field. We just don't have magnetic field here. Yes, unfortunately.
Because my question is going to be, does your inversion process make sure that this is zero?
Well, no. No.
I would be really impressed with that.
I would be impressed with that too. Yes. No. That's a whole other thing, and I haven't got to the point of. But I'm going to be effectively generating new training data with some ad hoc magnetic fields, because it's going to be one-dimensional. So, but trying a variety of inclinations and strengths of magnetic field, and then trying to apply this approach to it, because that's definitely going to produce degeneracy. So at that point, we can really see, outside of just test cases, how it handles degeneracy. But not there yet, because I'm still working on the forward code. Yes.
Same way that you were saying that it looks like a clustering algorithm. To me, it looks like a forward pass with a Bayesian probability distribution, and then a backward pass with a Bayesian probability distribution. So in other words, you have a prior assumption.
Yep.
And then you compute what's going on. Then you add some noise.
Yep.
To this thing in this direction. Then you go backwards, and then you have a posterior thing here, but then you also have a
Yep.
posterior thing here.
Is
that a way of looking at it?
It is. One of the ways I have kind of described it at times, and this is very vague, but it's a linear time MCMC. A linear time, in the our sampling is linear in time, but it's like an MCMC in terms of the posteriors that we get out. Markov chain Monte Carlo. Yeah.
And then the question of, so I was really struck by your last figures showing the distributions in the atmospheric parameters being so tight.
So these ones,
yeah,
yes. So these were these are not just tight. These are also gamma corrected to make the outliers appear more significant, because the model produces really tight distributions, and we wanted them to be more visible.
So the amazing thing is here is, if you look at a naive forward problem, then you have a null space in which any information doesn't propagate into the signal here. But furthermore, you also have ill conditioning, which means that a tiny change here leads to a much smaller change out here, or a larger change here. So what I'm impressed with is that those are fairly big, wide distributions, and those should correspond to enormous changes in the initial condition, or the first atmosphere.
So,
I'm interested in knowing how the conditioning is really working here.
The conditioning is this is the set of atmospheres that Radin will produce, and so it's not going to extrapolate to non-Radin and so a lot of those atmospheres that, if you were solving the forward problem traditionally, that you would end up with there aren't Radin atmospheres, because Radin won't end up in that state, and so there is an additional conditioning of Radin.
So you've added information. So in all these inverse problems, you have to add information.
Yes.
You've got no choice.
Absolutely.
Is adding it by looking at a collection of ill-posed problems, but in which you know what the conditions are.
Yes.
And then you're allowing that information to propagate both ways during the evolution.
And so that's why you only ever see Radin as a solution of an atmosphere. Yeah, because it's.
I understand what you did in my own language.
Yes.
This is all really
It conditions itself based on that assumption.
Yeah. And is the conditioning better than what you expect in some sense?
Yes, it was significantly better than what we expected.
Because to me it seemed like, for instance, if you just did a naive differential emission measure thing,
Yep.
the null space for that thing, if you have any oscillatory.
Oh, absolutely.
It's horrible.
Yes, absolutely. Yeah, I mean that's why you need such complex methods to reconstruct it. Yeah.
So I'm just intrigued. I mean, I guess I'm not really making much sense myself, but I'm just surprised that it does that well. I guess that's what I'm saying.
So were we, but we've.
In terms of the error bars on the
Absolutely. So were we, but to the best of our understanding, we've done it all correctly, and it appears to work that well. And the reasoning being, it's well conditioned off of the training set. And so this was trained with 81 Radin simulations, the version here. Now, we have done an additional 81 simulations of 500 time steps, of which the 20% were randomly extracted. We have also done, since then, around 280 additional Radin simulations, and we trained another version of it on those, and what we actually start to see, because we've used a broader variety of heating parameters in those simulations, is actually less good conditioning up in the corona, as you'd expect. It's not constrained by those lines. And the only reason we extend out so far, and it's with, we have 45 points below, I think it's 3 megameters, and then 5 points above 3 megameters. It's just there to look like a Radin atmosphere. The corona in this sense, because obviously those lines don't condition it at all. But yes, we start to see less good conditioning in the corona, as we'd expect. So yes, it is very much limited by the training set. But what we also see is that the transition region and below stayed very constant when trained with this much larger set of simulations, which was very pleasant to see, and something we were a little worried about.
So naively, I would say that the corona is very well constrained because of the initial modeling for it.
Absolutely.
Not because of any observation.
Yes. Entirely, yes.
That's a good way to look at this.
Yes.
Wow. and of course, in reality, we don't have any training set. We never know we don't have a thermometer, we can't measure.
Yeah.
What's going on in the height through the sun's atmosphere. So, and just one technical question: when you do the forward calculations,
Yep.
how are you handling the specific equilibrium?
No, we're using Radin's. So Radin's thing. So it's non-equilibrium populations, CRD lines. We're using the output from Radin. Yes. Because the statistical equilibrium is so close to meaningless in flares. Certainly for these lines. Magnesium, I think you can argue that magnesium 2 is very close to statistical equilibrium, no matter how hard you hit it. But for these, they're miles off. If you can even get statistical equilibrium to converge on these in any sensible code, which is another problem altogether.